Welcome to Ideas on Tap, presented by the Museum of Natural and Cultural History. I'm Lauren, and I'd like to start this evening by recognizing that the museum and the University of Oregon are located on Kalapuya Ilahi, the traditional indigenous homeland of the Kalapuya people. Following treaties between 1851 and 1855, Kalapuya people were dispossessed of their indigenous homeland by the United States government and forcibly removed to the Coast Reservation in Western Oregon. Today, Kalapuya descendants are primarily citizens of the Confederated Tribes of Grand Ronde and the Confederated Tribes of Siletz Indians, and they continue to make important contributions to their communities, to the museum and the University of Oregon, to Oregon, and to the world. We express our respect to the many more tribes who have ancestral connections to this territory, as well as to all other displaced Indigenous peoples who call Oregon home. To everyone joining us this evening, welcome. Although we might not be together in person, we do still want to hear your questions and your comments. During this evening's program, you can use the Q&A or chat features on Zoom and Facebook to reflect on the talk or add your thoughts, to engage with other viewers, and to ask questions of our speaker. I'll be collecting your questions across both platforms, and we'll get to as many as we can at the end. During the talk, we'll also post a link to a brief survey in the comments on both Zoom and Facebook. Please consider taking a minute or two to fill it out, even if you've already filled it out before. Your feedback will help us improve future virtual programs, and you'll be entered to win a $25 gift card to Viking Bracket Company, where the museum hosted our Ideas on Tap program prior to the pandemic, and where we hope to be back soon. If you enjoyed tonight's program, we're asking that you please consider making a secure, tax-deductible donation of $5 to $10 at the web address listed on the screen to help keep museum programs like this one accessible to all. That's giving.uoregon.edu/MNCHgift. Your donation directly supports the museum's educational programming, bringing science and culture adventures to Oregonians of every age and in every corner of the state. Thank you. Before we get started, I have a couple of upcoming museum programs to share with you. During the month of February, we'll be celebrating Charles Darwin's 213th birthday with natural history related programming, starting with tonight's Ideas on Tap. Then tomorrow, February 3rd, we have Fossil Finds from the Vault. Drop in anytime between 5 and 7 p.m. to meet museum paleontologists and to see fossils from the museum's collections. If you can't make it tomorrow, we'll be hosting Fossil Finds from the Vault again on Thursday, February 17th. And as always, you can stay until 8 p.m. on Thursday evenings, so come and explore Oregon's natural history at the museum. Then, from February 9th to 13th, Charles Darwin's birthday meets Valentine's Day during the museum store's annual Love Science sale. From barware to jewelry and books and toys, we've got a science-themed gift for every Valentine on your list. All non-consignment items are 10% off, or 20% off if you are a museum member or a UO faculty or staff. You'll also receive a free tote bag with your purchase of $50 or more. Admission to the museum store is always free. Finally, I hope you'll join me next month for another Ideas on Tap. Pheromones are nature's love potions, broadcasting chemical cues that shape sexual attraction and reproduction. Join Oregon State University biologist Robert Mason as he unravels the role of pheromones in the mating practices of red-sided garter snakes, including their famed snake mating balls. If you can't join us live, we'll post a recording to the museum's YouTube page the following day. And now it's my pleasure to introduce this evening's speaker, Dr. Samantha Hopkins. Sam is a professor in the Department of Earth Sciences and the Clark Honors College at the University of Oregon, as well as a curator of paleontology here at the Museum of Natural and Cultural History. Sam has an active field research program in the fossil-rich rocks of Eastern Oregon. Her research explores patterns and processes of the evolution of ecology in mammals, particularly in the context of changing landscapes. She joins us this evening to fill us in on Oregon's rodent of unusual size and some recently discovered fossils that, as of today, are on display here at the museum. Welcome, Sam.
Thanks, Lauren. Let me see if I can make the screen share work again. Okay, does that look all right?
It does.
Great, thanks. So I'm going to talk to you guys today a little bit about rodents of unusual size, and we'll talk a little bit about them in Oregon as well as in some other places. And just in case my pop culture reference isn't quite transparent to everyone, I'll try and change the slide. We'll see if it'll actually let me do that. There we go. If you've seen the movie The Princess Bride, then you know that one of the hazards that the heroes have to get through is the fire swamp. And the fire swamp has three main hazards within it. There are three things that make it so scary. There's the fire spouts, and there's the lightning sand. And then, of course, the final and most horrible of the hazards of the fire swamp are the rodents of unusual size. And here's the rodent from the movie, quite terrifying, not really a rodent. And I'll explain in just a minute why we can tell that this isn't really a rodent, but quite a nice Muppet here. And of course, it's, you know, one of the really memorable things about this particular movie. So what is a rodent? Rodents are the most diverse order of mammals. There's more than 2,000 species of them alive today. Exactly how many is subject to a little bit of discussion, but they represent something like 40% of all species of mammals on the planet. They occur on all the continents except Antarctica, and probably there are rats in our bases that make it so that there are rodents on Antarctica as well. And there's a huge diversity of different ecological forms, and in fact of similar ecological forms that have evolved on different continents among the rodents that live in those different areas. And when we think about rodents, there's generally this vision of them as little vermin-y creatures. But from a biological point of view, what a rodent is, we can recognize them using their some of the features of their skull in particular. So these big incisors, these big gnawing teeth that we see in rodents are one of the diagnostic features of the group, and one of the really obvious things that you can see. And then the other thing that you can really see in them is this difference between the front teeth, those big gnawing teeth, and then this distinct set of teeth in the back, the molars. And they're missing all the teeth in between, where we have a complete arcade of teeth. And what this means is that you can actually get functional separation between the teeth in the front that do a lot of the sort of gnawing, food processing, and often environmental interaction that the rodents do. And then those molars in the back, which really just chew up food, for digestion. And they actually have some interesting mechanics in the jaw that allow them to chew the incisors, to occlude the incisors against one another without making the molars touch. And then when the molars are touching, the incisors aren't. You can kind of see that in this specimen here, where the incisors out here in the front aren't quite in occlusion while the molars are sitting up against each other, right? So that allows them not to wear their cheek teeth when they're chewing on things, and then not to wear their incisors when they're processing their food. Okay, so really interesting adaptations that's led to this massive evolutionary radiation of rodents. Okay, but when we think about rodents, a lot of what we think about are like these little chipmunks and mice that we see here, right? They're pretty small animals. But today is the 2nd of February, and that means it's Rodent of Unusual Size Day. So today is Groundhog Day, and so it's a day that celebrates not the little rodents that we're so used to, but actually the bigger ones. So to give you a sense of where groundhogs fit in the great scheme of rodent sizes here, this is a plot of body mass in rodents versus the number of species of living rodents in that size. And you can see that most of them are in sort of this big lump here. There's lots and lots of them. There's hundreds of species in these size ranges, but groundhogs, Marmota monax, sit on the high end of this. And this is even more true than it looks from this particular plot, actually, because you'll notice that the x-axis down here, if you can see it, if your screen is small, you may not be able to read it. The x-axis of this plot is not exactly linear. It's not exactly the way you're used to seeing it. This is scientific notation because it's a log axis. And the reason we do that is that most of the rodents are really quite small, but the largest rodents, the rodents of the most unusual size, are so much bigger than those smallest rodents that if we just plot them on an ordinary linear axis, you know, sort of 0, 1, 2, 3, up to the size of those largest rodents, it's rather hard to look at. But we're not really as good at looking at this funny plot here and seeing exactly how big a thing is. And so I'm going to make this the ugly plot that we wouldn't normally look at so that you can see where everything fits in the great scheme of rodent size. Okay, so here it is on a more conventional plot. And you can see the range of body sizes in rodents. Most of them are really quite small, right? So if you look at the adult mass in grams here, most of them are within the range of maybe 100 to 1,000 grams, so a kilogram. Almost all rodents are less than a kilogram. The groundhog is pretty close to a kilogram. It gets right up around there. And so it's on the large end, okay? But you can see that rodents go all the way up to almost 50 kilograms. And so size in rodents covers a whole lot of range, right? So what do these really big rodents look like? Because they're unusual, right? They're rodents of unusual size. What do they look like, and how are they different from the rest of the rodents that we usually think about? There's several living species that are part of this rodents of unusual size club, right? And of course, the biggest of them, and the one that we're all most familiar with, that we're most likely to have a good visual image of, is this capybara here. Okay, capybaras live in South America, and they're common in grassy habitats there, where they graze and eat, you know, similar stuff to sort of small antelope and that kind of thing. And you can see they're, you know, not quite the size of a person, but pretty darn close, right? Leaning on that size range. Of course, in North America, we have our own rodent of relatively unusual size, which is the beaver. It's also, there's a second species of beavers in the old world. So the northern continents both have species of the genus Castor, of beavers. Beavers, you know, you may not think of exactly how large they are, but they're a pretty sizable rodent as well, right? So a distinct handful, and substantially larger than a groundhog, for example, right? So this is modern beavers are somewhere on the scale of you know, tens of kilograms, right? So weighty creatures. We also have some other relatively big rodents, like this porcupine here, right? So in North America as well as Africa, we have these big, unusually sized and also unusually prickly rodents, right? Big and ecologically pretty distinct from other things. And then of course, formerly just in South America, but now invasive over substantial areas of the world, are nutrias, right? Another rodent of unusual size. And if you're wondering why all the other pictures here have, you know, the rodents posing and being really cute with people and nutrias don't, if you've ever encountered a nutria, you know why, right? They're not exactly the most friendly rodents around, right? So I couldn't find any cute pictures of nutrias posing with people because they don't really like people very much, right? So again, tens of kilograms of rodents, right? So so when we think about rodents and we think about little ratty, squeaky things, little mice and that kind of thing, it's worth remembering that rodents do get substantially bigger than that, and occupy some much larger size roles than we necessarily think about them occupying. But of course, I'm a paleontologist, and these are just the living rodents of unusual size. And you have to ask the question, were the extinct ones bigger, right? We know the Pleistocene, the ice ages were full of really large rodents, and so, sorry, really large mammals. And so it's reasonable to ask, were there really large rodents to go with all of the other mammoths and mastodons and, dire wolves and giant saber-toothed cats and things like that? So did we have bigger rodents in the Pleistocene to go with all of these other big animals? And before the Pleistocene, right, the really large mammals that we know that went extinct at the end of the Pleistocene, for the most part, were rodents part of that, or were they just little squeaky things the whole time and didn't participate? In order to answer that question, we'd have to figure out first what we could use to determine the size of these extinct creatures, because of course, I'm quoting masses of extant things. It's pretty easy to take a living mammal and stick it in a scale and figure out exactly what it weighs. But of course, with extinct things, we've only got bits and pieces of them. We've got bones or parts of skeletons and teeth and jaws and things like that. And so figuring out how much they weighed requires us to do a little bit of scientific gymnastics. And so the way we do this relies on the fossil record of mammals, which is mostly made up of teeth and jaws. And so a whole series of scientists have developed equations to show the relationship between the size of the teeth in animals and their body mass, which conveniently is a pretty tight relationship when you look over the breadth of mammalian diversity. So this is an example of the kind of regression that you use, the linear regression that you use to determine these masses. Basically, if you measure the length of the tooth row in a rodent, so here's a rodent jaw just for an example, you can measure the length of the molar teeth in the back there. And if you take that measurement and you plug it into this regression, you can use the relationships that we have in living mammals to infer what the body mass would have been in the past, right? So if we have a jaw of a fossil rodent, we can use that to figure out the size that the rodent was. So we can answer this question of whether fossil rodents were bigger or more unusual in their size than the ones we have today, right? Did we have anything bigger than a capybara? Because if you've ever seen a capybara, you've probably seen one in a zoo or something like that. You know that they're really like dauntingly large rodent. And so anything that's bigger than that is going to really challenge our sense of what a rodent even is, right? So, so if we ask the question, were fossils bigger? Were fossil rodents larger than anything we have today? The answer is yes. And the story of the biggest rodent is one of those things that just gets everybody excited. Like, what's the biggest rodent out there? And one of the early contenders for this is this guy from South America. This is Neoepiblema, okay, an unfortunate species name or genus name. But this is a fossil rodent from South America. It's known from Venezuela and Brazil and Argentina and Peru, so several different spots in the record, the fossil record in South America. And if you take its jaw dimensions and you measure them and you reconstruct its mass, it comes out as being pretty similar in mass to a human being. So somewhere in the ballpark of 80 kilograms. And I apologize to those of you not familiar with the metric system. I'm going to use metric because this is what we do in the sciences. If you're trying to convert that in your head, get out your calculator, because a kilogram is about 2.2 pounds. So if you want a rule of thumb, then take the number in kilograms and multiply it by 2 and a bit. And that'll give you what may be more familiar to those of you who are accustomed to working in standard measurements. So Neoepiblema here is a Miocene animal in South America. So it's from about 20 to 15 million years ago. And you can see it's pretty big here, right? The scale bar on there is 50 centimeters, so that's half a meter. Remember, meters are kind of like yards, right? So, so this is more than a yard long rodent, right? This is something like, you know, substantial chunk bigger than a capybara. Okay, it's similar order of magnitude of size, but distinctly bigger. Okay, so already it's evident that the fossil record has things that are even bigger, which is great. But this was 20 million years ago, and we know that all the real excitement in giant animals is really in the Pleistocene. Okay, so maybe we can get a little closer. So around the time I finished up my graduate degree, there was a publication about this thing called Phobaromys Patterson Eye. And this was the next great excitement. This was, you know, the science paper about largest rodent ever. And the first paper that that described it estimated the mass as being about 700 kilograms, or about the size of a buffalo, which would be a singularly daunting rodent to encounter, right? Like, please don't run into that in a dark alley. Unfortunately, it turned out, and you can kind of see this from the illustration here, that Phobaromys, unlike modern capybara, carried its weight more on its hind limbs. You can see how the hind limbs of this thing are a little bit bigger than the forelimbs are. And they measured the diameter of the limbs rather than the tooth dimensions to infer the body mass. But because the mass was carried disproportionately on the hind limb, and there's some funny things about the way limb bones scale with respect to mass, they estimated a much larger mass than was actually true of Phobaromys. And so some subsequent studies that have used teeth and some other combinations of limb bones, as well as some other proxies for mass, have sort of pulled that mass estimate to a slightly less exciting 250 kilograms, which at the time was still the largest rodent we'd ever described. Okay, so, you know, something like 3 times the size of Neoepiblema there, and several times the size of a capybara, right? So, so here's your estimate. This drawing is probably slightly overestimated in size, but, you know, a whole lot of guinea pigs to make up Phobaromys, and several capybaras in order to get there. And this is later in time. So this is after Neoepiblema. It evolved from related animals. So this is late Miocene. So like, yeah, somewhere in the 10 to 5 million years ago, something like that. Best known from Venezuela, right? So, so they're getting bigger through time. That's kind of exciting. And just a few years after this came out, things just went all to crazy because they published this thing called Josephus degassia, named for Jose Artigas, who is a well-known figure in South American history. And this one, I think, really does earn the title of a rodent of really unusual size. So here's a picture of the skull of Josephus degassia in the hands of our very own Edward Davis, the curator here at the Museum of Natural and Cultural History. I swear we did not Photoshop this. This is actually the size of that skull. So it's the size of a small horse, right? The skull here is, you know, if you put a horse skull in his hands, it would look pretty similar, right? He's not a small man, and that is not a small rodent at all. And at least to date, this is the largest rodent ever described. So estimated mass is somewhere in the ballpark of 1,000 kilograms, right? So this is actually a rodent the size of a cow or a buffalo, right? It's really quite large. And this is getting into that sweet spot of the giant animals. It's sort of Pliocene to Pleistocene in Uruguay. So it's a, you know, by the time things have gotten good and cold and all the mammals are getting really, really big. Okay. So South America wins by just, you know, going away. Biggest rodent ever. This is where your real rodents of unusual size reside, right? What about North America? Do we have anything that even gets to enter into the competition? Well, we do, actually. You've probably heard of this. There's this animal, Castoroides, the giant beaver. And this is the biggest we've ever achieved in the North American record, something in the ballpark of 80 to 100 kilograms in size. And just to give you a sense of how this compares, right, here's our living castor. This is the European beaver, castor fiber, somewhere in the ballpark of 20 kilograms, right, next to a Castoroides, just to give you a sense of scale. Here are the skulls, just to compare them, right? So here's a modern castor skull, and then here's Castoroides. It's just not even in the same ballpark, okay? Just really quite large. Looks like about 4 beavers all put together would give you a Castoroides, right? And this thing is known from the Pleistocene of North America, okay? So again, in that giant animal sweet spot, right? Mainly from the late Pleistocene, we know these things. So I want to go back to that usual and unusual size concept. I want to go back to the plot of rodent body size and get a sense of where these guys fit relative to what we think of as rodents, so we can have a sense of how unusual they are in size. Okay, so here's our plot from before, right? There's the body mass of rodents against the number of species. Remember, most rodents, all the things you probably think of when I say rodent, are over here in this little size peak, just above 0 on this plot. And capybara sits out here in the ballpark of 50 kilograms, right? So that's why this line goes this far out in this plot. Capybara doesn't even hardly show up as a little blip on this plot because it's so much bigger than everything else that's around today, right? And there's your beaver, right? The 20 kilograms or so is right down here, right? So here are those fossil things. So here's Neoepiblema, the Miocene thing from South America, right? So it's in the ballpark of 80 kilograms, right? Here's Castoroides, closer to 100 kilograms. So for a little bit there, we're winning. But if we want to put the other two on, we actually have to totally redo this plot, right? They won't even fit. They're off the side of the thing, okay? So to do that, we'll just sort of squash all these guys down over here on the left so that we can make room, okay? And if we do that, there's Phobaromys, right? There's the what we first thought was the largest rodent ever. And to put it on at 250 kilograms there, we got to squash everything down a ways. And they're so far off that we have room. We can drop in a slightly derpy looking reconstruction of Phobaromys in there in the space in between Phobaromys and Castoroides. Okay, so they're all rodents of unusual size. Capybaras even are plenty unusual. Phobaromys is immense. But you'll remember that there's something even bigger. And in order to fit it on, I have to take my graph and I have to squash it all over again, right? We'll just shove all these guys over here. And on the same axis, on the same sort of stretched out axis here, we'll drop in Jose Artigas there. So Josephus degassia is so far out here. It's so much bigger. It's it's 4 Phobaromys, right? In the same way that Castoroides makes 4 of the modern beaver. And so that leaves us plenty of space to drop in a much less derpy illustration of majestic Josephus degassia galloping through a stream here, right? So really, really large rodents in the fossil record gotta make you wonder, what are we not finding, right? What do we not see? What are we missing in the fossil record, given that there's this immense gap in what we do know here, right? So, so I'm going to talk a little bit about filling gaps here, but I'm going to do that. I'm going to take us back to North America again. I'm going to talk a little bit more about our friend, the largest rodent in North America. Okay, yeah, it can't really hold a candle to Phobaromys and Josephus degassia, but you know, it's still respectable in its own right, right? So, so what do we know about Castoroides here? So Castoroides descends from a lineage of beavers in North America that are resident here since the Miocene, just as we saw that lineage of exceptionally large rodents evolving in South America. We have our own evolutionary sequence of Castoroides, beavers, of increasing size. And Castoroides actually is not particularly closely related to modern castor. It's related to some things called dipoides and some of their relatives that are common in the fossil record in North America. And in fact, in Eugene, or sorry, not in Eugene, but in Oregon, right? So dipoides are one of the common fossils we find in the Middle Miocene record in Oregon. And J. Arnold Shotwell, who was a paleontologist here, did a lot of collecting in Eastern Oregon, collected thousands of dipoides teeth. And dipoides is a fossil beaver that was sort of large squirrel sized. And in the Middle Miocene, that's kind of the size that they were. But as you go through the Miocene, you get to like 5 million years ago, that lineage of beavers starts to get really quite large. And by the time you arrive at the Pleistocene, you find Castoroides. And while they're right widespread up until the end of the Pliocene, so right until 2 million years ago, the record of Castoroides in the Pleistocene is actually not everywhere. So I'll show you a map just to give you a sense. And I apologize for the really pale little dots. The engine I used to generate this really wants all the Pleistocene things to be in pale yellow. And I didn't have a chance to make it brighter. So I have a solution to that, which is that I'm just gonna shade in the area over which it ranges. Okay, and you're gonna notice that these dots over here are all over on one side of this map. And in fact, if you shade in the geographic range of Castoroides, as we know it from the published fossil record of Castoroides, you'll see that it's kind of all over Eastern North America. Okay, they're really common in Florida. They're all up the Eastern seaboard. They're in, you know, Pleistocene faunas all the way even into the Great Plains. But they kind of have this hard limit here at the Rocky Mountains, right? So you'll notice that they don't really get into Colorado and into Montana and Wyoming and so forth. And you'll notice a distinct absence of dots indicating published records of Castoroides from anywhere west of the Rockies. So why am I, as a paleontologist at the University of Oregon, talking about Castoroides, right? This isn't a Western story. Why is this relevant to us in Oregon? And the answer is that the things that are published aren't necessarily everything that's out there. And I want to credit Mike Full in particular, who's a retired police officer who lives up in McMinnville. And he likes to go fossil collecting. And he emailed me some years ago and said, look what I found. And knowing that I have a fondness for fossil rodents, he sent me this image of a big honkin' rodent incisor. And and also invited me to come and see if I could find any more of this thing in the things that he'd collected up near McMinnville. And so I came to see him, and we went through his stuff, and he said, I think maybe this thing, got this funny looking, humerus here. I think this might be one of them too. And I said, oh yeah, that's another one. Those are Castoroides. And he said, oh, this is really exciting, right? What do we know about Castoroides in Oregon? And I said, nothing, right? And in fact, everywhere west of the Rockies, we know a bunch of nothing about Castoroides. So we'll just add a little something to that map. We'll put a big old dot right there, okay? Because all of a sudden, the range of Castoroides has just jumped the Rockies entirely. And it's evident that we have Castoroides here in Oregon. And if you want convincing, here's what we've got, all right? I will admit this is not a complete skeleton. This is not a complete skull. It's a little chippy, right? But we have 3 specimens all out of the Yamhill River near McMinnville of Castoroides. So these are the first Castoroides that we can say definitively have been found west of the Rockies. There are some, rumors of things, but in terms of fossils that actually we know where they came from. We have someone who, took the GPS position right in the place where they were and can say, absolutely, these are west of the Rockies. It's not like, a little bit of error one way or the other is going to make a big difference to this, right? There's nothing reported in the literature from anywhere west of the Rockies. So if you're having a hard time seeing what you're looking at, here's a chunk of incisor. You can see these big grooves that are on the front side of the incisors in Castoroides. This is one of the things that tells us it's Castoroides. It's also one of the things that absolutely tells you it's a rodent. Okay, nothing else has these ever-growing incisors like this. So there is a big old chunk of rodent incisor. This was the first thing that Mike sent me. It was like, ooh, oh yeah, that is definitely an incisor. Okay. Here's the humerus. It's a little battered. It was found in a river, so it's been rolled around a little bit. Okay, but here's the elbow part of the humerus, right? The upper arm bone. Okay, and here's where the deltoid muscle, the big muscle of the shoulder, attaches. And then here's the ball of the humerus, the part that goes into the shoulder socket here, right? So, so an entire humerus of one of these guys, and you can see it's really wide at the ends. Okay, this is distinctive in things that swim and dig and so forth. And so when we had just these things, then, we were feeling like we knew there was Castoroides here, but paleontologists don't get real excited about a scrap of incisor and a humerus. Nobody really wants to publish, the first Castoroides west of the Rockies on that basis. It's like, yeah, well, what if you're wrong? What if it's some other rodent? Like, what are you doing? So a couple of years ago, Mike sent me an email and said, look what I found. And it was this, it's this jaw, okay? It's a little bit beat up again, but you can see here's all the molar teeth right here in the tooth row. And here's a piece of incisor sticking out of the front of the jaw. And then the jaw muscles will be back here. You're looking at the inside of the jaw, sort of from the inside of the mouth here. So here is a jaw of Castoroides, and paleontologists, as I said, love jaws and teeth. So at this point, we are feeling good. We are pretty confident in what we're looking at, right? So here it is. Here is the rodent of unusual size in the Oregon record. Okay, so we're not left out anymore. And in fact, we've beaten all the other states west of the Rockies to a rodent of really exceptionally unusual size here. And finding these pieces of Castoroides really tells us that that this is something that must have been in the area. And the question now is just exactly how widely did they range? How much of this area had these giant beavers in the fauna? And then, I mean, the other thing that we want to think about when we find something like this is what does it tell us about the way the ecosystem was? What have we learned about Oregon besides that it had a really exceptionally large beaver in it? Well, one of the things that's interesting about this is that Castoroides is not just a bigger version of castor. Okay, so modern beavers, as we know, they build dams, they cut wood, they live in this ecologically really unusual way, right? Part of how you make them such a really big rodent is that they do things really differently from a lot of other rodents. So when we look at Castoroides, is this just more of the same? It really isn't. It's not just a bigger version of it. So if you look at Castor here, you can see those incisors, those teeth that rodents all use to interact with their environment that are really great indicators of what they're doing ecologically. In Castor, they're relatively flat. You can see they're sort of compressed and flattened. They have a really flat front face with no ridges at all on them. It's just a chisel for cutting wood, right? And if you look at the incisors on Castoroides, just like that one that I showed you a picture of that we have, they're much rounder, they're sort of more columnar in shape, and they have all these ridges running longitudinally down the tooth, all right? And then you can also see that the way that the incisors protrude from the skull, they're much more protrusive here, right? There's the jaw is sort of pulled back around those incisors, and they're kind of big and prominent and protruding in a way that suggests slightly different use of those incisors. Now, there was a great study that Natalia Rodzinski did back in the early 2000s that showed that Castoroides were nested within the group of beavers that were woodcutters. We have definitive evidence that Dipoides, which I told you is one of the ancestors of Castoroides, also cut wood. We actually have cut wood in assemblages that have fossil Dipoides where the shape of the teeth matches the shape of the teeth marks on the stumps in the fossil record. And so we know the ancestors of Castoroides were woodcutters. We know that modern Castor is a woodcutter. So we believe that Castoroides did cut wood. But the shape of these incisors indicate that probably did it in some ways that are different. They might have been pursuing different trees or different sizes of trees. They might have been processing the wood differently. You know, we know that modern Castor chews the bark off of the trees and eats the cambium, the soft tissue on the inside of the bark. You know, maybe Castoroides was processing things differently and eating different parts of the tree, right? Certainly, they could have taken much larger trees down. The other thing I want you to look at, and this is a nice reconstruction, the sculpture that someone has done of Castoroides, although the face is maybe a little bit more beavery than is suggested by the differences in the skull here. But one of the things I want you to notice is that their tail is not that big flat paddle that we're used to seeing that's so distinctive of modern beavers. So this is more like a muskrat's tail. And this is based on work that Josh Samuels did, looking at the shape of the tail vertebrae in Castoroides. Conveniently, we have entire skeletons of these things, not from Oregon, but from other places. And that demonstrated that while these things were certainly semi-aquatic like their living relatives, their tails would not have been that same big paddle. You get really distinctive changes to the vertebrae of the tails of Castor that support those big paddly tails that they use to make noise and signal one another and that kind of thing. And so the other thing that's probably pretty distinct about the ecology of Castoroides is the way they swim, right? And so that may suggest that our concept of Castor as these, you know, pond building, wood cutting, dam building creatures may not be something you want to directly sort of rubber stamp onto Castoroides. It's not like they're necessarily just going to be bigger and make bigger ponds and bigger dams and, oh my goodness, damming the Columbia River or something like that in order to, you know, make a big enough lake to accommodate a beaver this big. Instead, you might have a semi-aquatic habit that's less dependent on this sort of dam building behavior that might be more swimming around in rivers or something like that along the lines of a nutria or a muskrat. And that wood cutting might be processing wood in a really different fashion. Right? So, so I know this is just a teaser. I know this isn't really, you know, showing you a big, you know, change to our understanding of Castoroides. But a lot of what I wanted to do here was really just point out that we have something in the Oregon record that's going to change the way we look at the ecology of the Pleistocene of Oregon. And then it happens to be a really exceptionally large rodent. So more to come on this. And you'll hear more about it in the coming few years as we work this out. We've just started processing this fossil. We've scanned it. We're about to go and get it dated and figure out exactly when these things were here. So keep your ear to the ground, and we'll have more to tell you about this. The last thing I want to do is thank all the people who have been involved in this. It's amazing how 3 little fossils pull a whole bunch of people in to really understand what they're telling us. Mike Full, of course, first and foremost as the finder of the fossil. Greg McDonald, formerly of Hagerman Fossil Beds, formerly of the Bureau of Land Management, now retired, is actually taking the lead on describing these fossils. When he was at Hagerman, he did a whole lot of work on Castoroides, and so he's kind of our head man in charge, thinking about Castoroides and what we can learn from the fossils that we do have here and how they relate to other finds of Castoroides that we might have made in the past, more complete material and so forth. Leonard Finkelman has been working with us on this, and I really appreciate the work he's done on some of the Yamhill River paleontology there. We did our imaging at the Knight campus, which kindly allowed us to image the fossil. We have a CT scan of that jaw that's just really exciting, and is showing us the morphology of the inside of these teeth. We haven't really dug into that yet. And then Edward Davis and Natalia Robzinski and Josh Samuels have contributed to a lot of our discussions about this. And Elizabeth White, I want to thank for taking photographs of those fossils that made it actually possible to see them. They're kind of chunky and hard to understand. So with all of that, I will thank those people and thank all of you for coming, and I'll be happy to take questions.
Thank you so much, Sam. That was great. I do want to remind everyone that if you have questions for Sam, you can drop them in either the Q&A or the chat. And if you're watching on Facebook, you can add them to the comments there, and we do collect questions from both platforms. I also want to remind everyone that the fossils that Sam was showing, the photos of the new Castoroides, are on display here at the museum now. So you should come on down, check them out. We are open Wednesday through Sunday, 10 a.m. until 5 p.m. and until 8 p.m. on Thursdays. So with that, we'll jump into the first questions that we're getting. Someone is saying that a lot of little tiny modern rodents like mice and rabbits have lots and lots of babies. Was this true of the big ancient mammals?
That's a great question. The best analog we have for that today is actually the living capybara, right, which get up into similar size ranges to these things. And certainly capybaras have lots of babies. So they have litter sizes. I want to say somewhere in the like 6 to 10 range. I'm pulling that number sort of out of the back of my head. But if you Google up photos, you'll see mommy capybaras with a whole little mess of babies. So they are expected to have that same kind of capacity to reproduce really rapidly. Yeah.
Someone else is saying that they were recently at agate fossil beds in New Mexico, and they were fascinated by the burrows of Paleocastor, which is approximately at the western edge of Castoroides' previously known range. What's the relationship between those two?
So Paleocastor, the burrowing beaver that produces those demonelics, those cool spiral burrows, is actually pretty distantly related. So they're both in the family Castoroides, but there's basically 2 big lineages within the Castoroides. There's a whole group of burrowing beavers that are really diverse during the time that agate fossil beds was being deposited. So from the Oligocene about 30 million years ago into the early Miocene about 20 million years ago, something like that. And that's sort of side A of the Castoroid family tree. Castoroides is from the other side, which is all of those all of the swimming and wood cutting beavers. So it's about as far from Castor as you can get within that group. So, lineage with Dipoides that leads to Castoroides is sort of one side of it, and Castor is over on the other side. But Paleocastor is like level 2 separate from the aquatic ones, but great question.
Do you assume that the big Castoroides will be eventually found between like the Mississippi and everywhere else in the West Coast? Are they just missing from the record right now, or
That's a
do
good,
we have
good
a
question.
unique one here?
Yeah, it's hard to know what we will find. I suspect that Castoroides, being the kind of semi-aquatic animal that it is, probably is not going to be living up in the sort of high elevation environments in the Rockies and the Pleistocene. And remember, a lot of those are glaciated off and on, especially the more northern latitudes through that time. And so, my guess is that Castoroides is in Western Oregon because it's got large river systems, right? And so it's the kind of place where a really large semi-aquatic animal has kind of room to roam, right? And so I wonder if you had it, if you were out there in the Pleistocene wandering around the landscape, taking note of the animals you saw, I think you'd probably see a big old Castoroides desert as you went over the Rockies. And it's only when you get the big river systems in the west, near the West Coast, that you would pick up Castoroides again. One of the interesting questions there is whether our Castoroides is the same kind of Castoroides as they have east of the Rockies. And unfortunately, with just a jaw, we don't have quite enough information to figure out what species it would be and whether it could be a different species from the ones that we see east of the Rockies. There are two species over there, one sort of southern and one sort of northern species, and they're distinguished by features of the skull. So until we find that skull, we're not exactly sure whether what we've got is the same species or not. But we can say it's the same size as both of the other species. So the two species existing of Castoroides are pretty similar in size, and that's why we can't distinguish them with just a jaw. But our jaw falls within the size range of the other ones. So if it's a different species, it's not significantly different in size, right? But it could have been separated by the Rocky Mountains and just be doing different things. And I can see a few of the other questions in the Facebook chat are sort of asking about where these things would have been and how they got here. You can speculate about them following rivers around, right, in these large rivers to get there. I suspect if you were looking for the connecting Castoroides, if I were a Benton woman, I'd be looking down on a southerly route, right? It's possible that in interglacial times during the Pleistocene, when the glaciers retreated to the north, there could have been a path sort of working your way across Canada there. But it would definitely be, it'd be interesting to figure out where they are in between. I would expect to see some kind of connections. The interesting thing is that their ancestors are over a lot of this. So Dipoides ranges all in between, right? And it's only the really big ones. It's only that Castoroides that's really just missing otherwise through the Rocky Mountains.
So you made a joke about nutria at the beginning with the photos that you had. Someone's wondering who you think would win in a battle, nutria or Castoroides?
Well, I mean, Castoroides is about 4 times the size of a nutria. So, generally, I'm going to take the chances of Castoroides in that one.
Someone is also mentioning that teeth oftentimes can reflect diet, and whether you can tell anything about the changing diet of beavers over millennia based on their teeth.
So from what we can tell, pretty early in the evolutionary history of the lineage leading to Castoroides, they started eating really abrasive food, and that's probably things like the bark and cambium and leaves that they eat today. So they're pretty specialized vegetation eaters. And that's true of all of these really unusually sized rodents, right? So rodents of unusual size are almost all folivores, which isn't really, so leaf eaters, right? And that's not really surprising when you look at mammals in general, right? The biggest mammals are mostly big grazing things. And so these guys aren't grazers, but they are, eating an abrasive diet. They're eating low quality forage that takes time to digest and to get the most energy out of. And so, even when you go back to Dipoides, you already have the cheek teeth, the back teeth of the jaw, are really, really high crowned. They're higher crowned than horse teeth are. So they're better adapted to abrasion even than horses, which eat a nothing but grass type diet, right? So we have a pretty good idea that Castoroides and its ancestors all the way back to the Middle Miocene, to 15 million years ago, were eating pretty much foliage and nothing else.
So branching out a little bit, someone is asking whether there were any otters of unusual size during Pleistocene.
Oh, well played. I don't think that otters get quite so extraordinarily large. There are badgers of unusual size in the late Miocene, so you do get pretty big badgers. But honestly, when you think about size, we're so used to thinking of those top predators as like the winners, the killers, right? They're going to beat everything else. But the carnivores are like small potatoes in the realm of body size, right? The herbivores always win where body size is concerned, right? You can just pick up so much low quality forage, and you don't have to be fast, you don't have to chase down your food, it's just everywhere, right? And the largest mammals gain this invincibility, right? This invulnerability against predators. And so if you're looking for mammals of unusual size, it's all herbivores, man.
So we have time for just a few more questions. So we're going to go to another kind of fun one. Someone is asking what your favorite extant rodent of Oregon is.
I feel like I'm seeding the questions here. I'm talking here about Castoroid beavers, right? Beavers as most people know them. But my favorite living rodent in Oregon is actually the mountain beaver, which is almost completely different from these things. It's not even in the same part of the rodent family tree. It's way over with squirrels. So mountain beavers are not beavers and mostly don't live in mountains, but they're also called boomers. They live up in the Coast Range in Oregon. And they do eat low quality forage. They eat foliage like these guys do, but they dig holes rather than swimming so much. So they're my personal favorites.
So do you have a favorite extinct rodent then too?
Well, yeah, I mean, that's the horned gophers. So the close relatives of those mountain beavers. Some of them were extremely adapted for digging holes, and several of them put horns on their nose. So if you want to see what that looks like, they have some great models of those in the John Day Fossil Beds Visitor Center over at Sheep Rock.
Perfect. And so we have someone asking about the newly found fossils and whether their features similar to the one from the East Coast might be resulting from convergent evolution. And maybe if you want to explain what that is for our viewers as well.
Absolutely. So the question is, are these rodents looking like Castoroides, even though they're not actually particularly closely related? Are they doing similar things and so evolving similar morphology? And that kind of thing can happen, but it's not terribly hard to spot, because it's a bit like, if you don't have the right, if you need to make a tool to do something, and you're going to go down to your shop and you're going to sort of like modify the things you have and cobble something together, you're going to make it in a way that serves a similar function, but you're going to make it out of whatever stuff you have around. And evolution is like, always making up new tools, right? It's always taking what it's got, and then variation in those characteristics sort of is applied to solving the same problem. So convergent evolution always makes things that kind of look similar but when you really look at the details, it's clear they're made out of different stuff. And man, if you look at this jaw, I could give you photographs of jaws from Florida, and it's no different at all from, known Castoroides specimens. And we took measurements on every tooth of this jaw. We've measured everything we could see to measure on there, and it's well within the range of existing Castoroides, even down to those little squiggles on the tooth enamel. It looks just like Castoroides from the other side of the Rockies.
Well, we have reached our time for this evening, so I want to thank Sam so much for joining us and giving us such an awesome talk tonight. It was so fun to have you here with us. I want to thank everyone who tuned in and who continue to join us month after month as we stay virtual. I look forward to seeing everyone in person. I hope everyone is staying well, and I hope we'll see you back here next month for another Ideas on Tap.
Thanks, everybody.